Imagine a room filled with space heaters, all running at full blast. Inside data centers, countless processors generate enormous amounts of heat. These processors are constantly working, crunching numbers. This activity generates heat, a byproduct of their efforts. Instead of wasting that energy, what if we could capture it? Microfluidics can turn this wasted energy into a valuable resource. Microfluidics manipulates fluids in channels thinner than a human hair. Imagine a network of miniature pipes, invisible to the naked eye. These channels can be etched onto chips, creating intricate pathways. In processor cooling, these channels are filled with coolants to absorb heat. Like veins in our bodies, microfluidic channels carry away heat. Microfluidic cooling systems are integrated directly onto computer chips, creating a closed loop for heat dissipation. These systems typically consist of a microfluidic heat sink, a small device with a network of microchannels etched onto its surface. The processor sits atop this heat sink, its heat dissipating into the coolant flowing through the channels. Imagine a series of tiny waterways carved into the surface of the processor itself. As the processor heats up, the coolant flowing through these waterways absorbs the excess heat, carrying it away like a miniature river system. This efficient cooling method keeps the processor operating at optimal temperatures while also capturing the waste heat for later use. The choice of coolant is crucial in microfluidic cooling systems. Different fluids have different heat capacities, meaning they can absorb varying amounts of heat before their temperature rises significantly. Water, with its high heat capacity, is a common choice. Other coolants include specialized liquids designed for their thermal properties. Think of coolants as sponges that soak up heat. Some sponges are better at absorbing water than others, and similarly, some coolants are more effective at absorbing heat. Selecting the right coolant is essential for maximizing the efficiency of the heat recovery process. A highly efficient coolant can absorb more heat, allowing for more energy to be captured and reused. Section 5. From chip to radiator, delivering the heat. Once the coolant has absorbed heat from the processor, it needs to be transported to where the heat can be used. This is where the concept of a closed-loop system comes into play. The heated coolant is pumped from the microfluidic heat sink to a heat exchanger, a device that transfers the heat to another fluid, typically water, used in a building's heating system. Imagine a network of pipes connecting the processor's cooling system to a radiator in your home. The heated coolant acts as a delivery service, carrying the heat from its source to where it's needed. This closed loop ensures that the coolant is continuously cycled, absorbing heat from the processor and delivering it to the building's heating system. Section 6. Thermodynamics, the science of heat transfer. Heat naturally flows from hotter objects to colder ones, and the efficiency of this transfer depends on factors like temperature difference and thermal conductivity. Maximizing efficiency is crucial for energy savings and environmental benefits. Think of heat transfer like a relay race where the baton represents the heat energy. The more efficiently heat is transferred, the less energy is wasted. Section 7. Scaling up. Challenges in large-scale implementations. While the concept of using microfluidics to recover waste heat from processors is promising, scaling up the technology to meet the demands of large data centers presents significant challenges. Data centers house thousands, even millions of processors, generating immense amounts of heat. Managing this heat effectively requires complex networks of microfluidic cooling systems and efficient heat transfer mechanisms. Imagine trying to connect thousands of miniature radiators, each cooling a single processor, into a single cohesive heating system. This requires careful planning and design to ensure that the heat is collected and distributed efficiently. Additionally, the system must be robust and reliable, capable of handling the demands of continuous operation. Section 8. Data centers, urban heat islands with a purpose. Despite the challenges, there are already successful examples of data centers using waste heat to heat buildings. In Stockholm, Sweden, several data centers are capturing the heat generated by their servers and using it to heat homes and offices in the surrounding area. This innovative approach not only reduces energy consumption, but also helps to mitigate the urban heat island effect. Think of data centers as potential heat farms, strategically located within cities to provide a sustainable source of energy. By capturing and reusing the heat they generate, These data centers can become valuable assets in the transition towards more sustainable urban environments. Section 9. Environmental impact: reducing our carbon footprint. The environmental benefits of recovering and reusing waste heat from processors are significant. Data centers are massive consumers of energy, and a significant portion of this energy is wasted as heat. By capturing and using this heat, we can reduce the demand for fossil fuels, lowering greenhouse gas emissions, and mitigating the impacts of climate change. Think of heat recovery as a form of recycling, but instead of materials, we're recycling energy. By reusing the heat that would otherwise be wasted, we're reducing our reliance on new energy sources and minimizing our impact on the planet. Section 10. Control systems: keeping the heat flowing smoothly. Effective heat recovery relies on sophisticated control systems to regulate the flow of coolant and ensure optimal heat transfer. These systems use sensors to monitor temperatures at various points in the network, adjusting coolant flow rates and heat exchanger operation to maintain desired temperatures and maximize efficiency. Imagine a thermostat for the entire heat recovery system, constantly monitoring and adjusting to maintain a comfortable temperature while minimizing energy waste. This intelligent control system ensures that the right amount of heat is delivered to the right place at the right time, optimizing both comfort and efficiency. Section 11. Beyond buildings: expanding the reach of heat recovery. The applications of microfluidic heat recovery extend beyond simply heating buildings. The captured heat can be utilized in various industrial processes, reducing energy consumption and costs across different sectors. For example, the heat can be used for water heating, drying processes, and even in agricultural greenhouses. Think of processors as portable heaters, their waste heat repurposed to provide warmth and energy for a variety of applications. This versatility opens up exciting possibilities for utilizing this previously untapped resource in innovative and sustainable ways. Section 12. Future integration: a smarter, more sustainable future. Looking ahead, microfluidic heat recovery systems can be integrated with renewable energy sources and smart building technologies to create a more sustainable and efficient energy landscape. Imagine a building that uses solar panels to generate electricity while simultaneously capturing waste heat from its data center to provide heating and hot water. This integration creates a synergistic relationship between different technologies, maximizing energy efficiency and minimizing reliance on traditional energy sources. The building becomes a smart ecosystem, optimizing its energy usage and reducing its environmental impact. Section 13. Cutting-edge coolants: nanotechnology in action. Advancements in nanotechnology are leading to the development of even more efficient coolants. Nanofluids, liquids containing suspended nanoparticles, exhibit enhanced thermal conductivity compared to traditional coolants. These nanoparticles act as tiny heat carriers, significantly improving the heat transfer capabilities of the fluid. Imagine these nanofluids as supersponges, capable of absorbing and transporting even greater amounts of heat. This enhanced heat transfer efficiency translates to more effective cooling for processors and greater energy recovery potential for heating applications. Section 14. Ethical considerations: a responsibility to our planet. The widespread adoption of microfluidic heat recovery technology carries significant ethical and societal implications. As we develop increasingly energy-intensive technologies, we have a responsibility to minimize their environmental impact. Utilizing waste heat is not just an engineering challenge, but an ethical imperative. Think of heat recovery as a form of upcycling on a global scale. By finding innovative ways to utilize waste energy, we are taking responsibility for our actions and working towards a more sustainable future for all. It is a testament to human ingenuity and our commitment to safeguarding our planet. Section 15. The road ahead: continued innovation in heat recovery. The field of microfluidic heat recovery is constantly evolving, with ongoing research and development efforts focused on optimizing system designs, exploring new materials, and improving control mechanisms. As our understanding of microfluidics and nanotechnology advances, we can expect even more efficient and innovative heat recovery solutions. Think of this field as a continuous journey of discovery. with each new breakthrough bringing us closer to a future where waste heat is no longer wasted but harnessed as a valuable resource. It is a testament to human ingenuity and our unwavering pursuit of a more sustainable and energy-efficient world.